In this lecture, we'll be discussing the vibrational rotational spectroscopy or the effect of vibrations in a rotating molecule. So far, we had considered rotational transitions to be independent and vibrational transitions to be independent. Now, if that is true, let's say we are considering a situation wherein vibration and rotation are independent of each other. So that means the energy due to the vibration and rotations can be written as energy due to vibration plus energy due to rotation. Now this would mean this is mu e 1 minus xc plus let's say this is 2b j plus 1 or let's break it down. So let's say this is v plus half mu e minus v plus half whole square mu e xc plus bj j plus 1 minus dj square j plus 1 square and other terms. Now obviously this is coming from the non-rigid rotor approximation, and this is coming from the enharmonic oscillator. Now we know that the value of d is almost 10 to the power minus 3 of b. So that means, and the higher terms go on decreasing, so we can consider their contribution to be very negligible, and we can actually remove this. So what we are left with is only this part. Okay, fine. Now what are the selection rules that you can have? Now on solving the transition probability, the selection rule that you get is delta v is equals to plus minus 1 and delta j is also equals to plus minus 1. That means delta v behaves like a simple harmonic oscillator wherein there is only allowed transition to one higher energy level and one lower energy level, whereas delta j is same as it was in rotational energy levels, restricted to only plus minus 1. What effect will it have when we want to see delta E? Now delta E for this selection rule becomes 1 minus 2 xc. Now I am considering delta V equals to plus 1 here. We are considering the case where absorption takes place. Okay, so before that, let's visualize what we are trying to do. Let's say these are two vibrational energy levels which has smaller rotational energy levels. And okay, we considered the vibration and rotation are independent of each other. This in principle is known as the Born-Oppenheimer approximation. So this would mean that during the vibrations there are no rotations taking place, and during the rotations no vibration is taking place, and that is why during the rotations we are considering the bond length to be fixed during the rotations, not the vibration. During the rotation the bond length is fixed. That is why we are considering the rotational constant in both the vibrational energy levels for the rotational states remains same. This is something which we'll see why this is wrong. Okay. Now, when we're talking about delta V plus minus 1, that means the transition can take place from here to here. Let's say this is V equals to 0, V equals to 1, and we are interested in fundamental transition only. Let's say this is J equals to 0, 1, 2, 3, 4, J dash equals to 0, 1, 2, 3, 4. Okay. Now, when delta J is plus minus 1, transitions like this can take place: 0 to 1, 1 to 2, 2 to 3, or 1 to 0, 2 to 1, 3 to 2. These kind of transitions can take place for delta J equals to plus minus 1. Okay. So what will be the formula for delta E then? Now we know for delta J plus minus 1 we get 2b J plus 1. Let's say I'm considering the case of delta J equals to plus 1. So this will be plus 2bj plus 1. And if I'm considering the case of delta j equals to minus 1, this will simply be minus 2bj plus 1. Okay, fine. So that would mean I can rewrite this formula as mu e 1 minus 2xe plus minus 2bj plus 1. So 2bj plus 1 will get deducted from this quantity. So that means you will see that you have a very large peak. I mean, you will have some peak, let's not say this is a large peak, that you will have some value of this from which this part is deducted and this part is added, depending on whether it's delta j is plus or minus. So what is the kind of graph that you will see? Oh, I took too much of space. So what you will see is okay. Now this mu e 1 minus 2xe is here, and this is known as the band center or band origin. This is the origin of the band, plus bj 2bj plus 1 and minus 2bj plus 1. Now for the plus, obviously this corresponds to 0 to 1, 1 to 2, 2 to 3, 3 to 4, 5, 6, 7. Similarly here it is 0 to 1, 1 to 2, 2 to 3. It remains the same. Okay, I missed one. So both have the same pattern. It's just that from one origin they are on two different sides. These lines are known as R lines. These lines are known as P lines. And how are they named? They are named delta j equals to minus 2, minus 1, 0, plus 1, plus 2. So this will be Q, P, O, R, S. In this lecture, we'll only focus on P and R, but in the later lectures, we'll focus on Q and S when we discuss about Raman spectroscopy. Now, why there is no peak at band origin center or when delta j equals to 0? Now, delta j is 0 means there is no rotation taking place in the molecule. It remains in the same energy level, and that is not possible. I mean, that is possible, but that is not what we are studying. We will not be able to detect that. So that is why we don't see any peak at the band center. Okay. That's all I wanted to discuss about the Born-Oppenheimer approximation applied vibrational rotational spectroscopy. But as we know, whenever there is vibrational transition taking place, now during one complete rotation, almost 200 to 300 vibrations take place. So that means in one complete rotation of this molecule, both the ends, let's consider this is diatom, both the atoms are vibrating almost 200 to 300 times. That means the vibration and rotational transitions or their energies are not independent of each other. Why? If they are vibrating during the rotation, then the bond length is changing, and if the bond length is changing, the rotational constant will change, and if the rotational constant is changing, the energy of the rotational energy levels will also change. So that means this is going to get invalid, which is what we know as a breakdown of Born-Oppenheimer approximation, which we had seen in case of vibrational spectroscopy also. Now that will show some effect on these energy values, the kind of transitions that are allowed, and the kind of the graph that we are going to get, which we'll see now. So one thing I forgot to mention was that in the spectra that you are getting, the difference between two rotational peaks is still going to be 2b, except for the first ones, which are in the R and P. For them, it is going to be 4b, because there is no peak at the middle, that is missing. Okay, now we'll consider the breakdown of Born-Oppenheimer approximation. Now this breakdown means initially we had considered that the rotational constant in the rotational energy levels at the ground vibration state and the first excited vibration state remains the same, but this is not going to be true now. Okay, so because the bond length is constantly changing, your rotational constant is also going to change. Now, rotational constant can be represented by B naught is equals to BE minus alpha V plus half. If I am not wrong, I think this should be the formula. Now, BE is the equilibrium rotational constant, that means at equilibrium bond length. Now, the molecule is never going to have B naught equals to BE, that is because this value at even V equal to 0 will have half. So that means half alpha will get reduced. So that means this is never going to be the case, and if this is never going to be the case, we'll never see a spectra that we had seen in the last few minutes. So let's say if we have the breakdown of Born-Oppenheimer approximation, then what our energy levels are going to look. So the energy from the vibration part is still going to look the same. That means it will be V plus half mu E minus V plus half square mu E xc. But for the rotation part, now you cannot simply write that it is 2bj plus 1, or let's say delta E is 2bj plus 1. That is not going to be true. Why? Because B is not same in both the cases, in both the states. What do I mean by that? Let's say these are the energy levels. When it does transition to here, the B here is different from the B here. Let's say this is B0, this is B1. So if B1 and B0 are different, you cannot come to this formula. So that would mean this will be B dashed J dashed plus 1 plus minus B naught, or let's say let it be just B J plus 1. Now in this case I have considered delta J to be plus 1. Now the selection rules. Now for selection rules, delta V can be anything plus 1, plus minus 1, plus minus 2. Okay, even in the case of the previous case that we had seen, delta V can be anything plus minus 1, plus minus 2, but for our simplicity, we had considered only to be plus 1. That means we had seen the fundamental transition, but it can be other values also. But delta J is still going to be plus minus 1 only. Okay, now if this is true, delta E is going to be, in this case I am considering fundamental, that means V equals to 0 to 1, and this can be rewritten as in this case, I am considering delta J equals to plus 1. That means J dash equals to J plus 1. The other way around can also be written wherein delta J equals to minus 1. The formula simply will be okay. Now in this case, the only difference is that J is equals to J dashed plus 1, if I am not wrong. Okay, now the problem with these two formulas is that you cannot directly arrive at this formula, and I have looked at 2 or 3 books. This is one which is given in Banwell, but a different formula is given in Barrow. Now it doesn't matter which formula you are using, the physical significance or the physical analysis that we can do from here remains the same. What is that we'll see. Now see, one thing you have to understand, that B dashed and B is at the lower energy level, B dashed is at the higher energy level. Energy level means this is V equals to 0, this is V equals to 1. As the vibrational energy level increases, the bond length also increases. And if the bond length is increasing, inertia is increasing. And if inertia is increasing, rotational constant is going to decrease. That means B1 or B prime is going to be less than B. And if that is true, this quantity is always going to be negative, right? So that means these parts are always going to be negative. Fine. If that is understood, so we know this is a constant, this is a constant. The only thing that is going to make a difference is this. And why? Because it has a plus sign, this has a minus sign for delta J plus 1 and delta J minus 1. Okay. And how would it look like? Let's say maybe we can simplify this as okay, wherein m is equals to j plus 1 for delta j equals to plus 1 and m equals to minus j plus 1 for delta j equals to minus 1. From both these we can make a common formula. But how is the plot going to look like, or how is the spectra going to look like? Okay, so okay, the pattern of the spectra is still going to remain the same. There is going to be no change in that. But what is the change that you're going to see? Now let us consider the case of j plus 1. That means I'm considering this case which are R lines, this case which are P lines. Okay. In this case, in the R lines, there is some increase and there is some decrease because of this negative part. Okay. So that means in this entire part, there is going to be a decrease. That means, let's say, without this, these lines would look something like this. But because of this, the lines will now come closer. So there is a shrinking of lines, shrinking of space, or lines come closer in the R lines. Now, if you take the case of P lines, in the P lines, this is negative, this is negative. So actually the spacing is going to increase. Okay. So from here, you have some part, you get some line, and that line is again shifted to the negative side because everything is happening to the negative side of this. So that means there is a spacing out of lines, or lines go far. Now this is the physical interpretation or the analysis that we need to make from these formulas. It's not very much important to know what is the exact formula, but the significance that it holds. Okay, we'll take one example and see what is the effect of isotopic substitution. Let's say I'm considering the case of CO. CO can be 12 CO or 13 CO, and I'll do it in the same plot. So the 13 CO, this is fine. This is how the nature of the spectra is going to be. Now 13 CO would look something like this. Okay. The nature of the spectra still remains the same. What has happened is the peaks have become very, very much close. And why is that? Because in 13C, the reduced mass increases, inertia increases, B becomes small, so the peaks will come closer. Okay. Or in other terms, the effect of these are going to be lesser in case of 13CO. The second thing is, if you see the height of the peaks. Now the height of the peaks is less because the intensity is less. Now why is the intensity is less? Because the abundance of carbon 13 is almost like 1%. So that means their intensity is going to be less because of the less abundance or less population. Okay. Now let's take a look at the questions that we have. We have 2 to 3 questions from NET and GATE. So the first question we have is from December 2014 NET. And the question says, if the bond length of a heteronuclear diatomic molecule is greater in the upper vibrational state, the gap between the successive absorptions of P branch. That means we are considering the P lines. What is it going to be? Increases non-linearly, decreases non-linearly, increases linearly, or decreases linearly. It is never going to decrease. The gap is going to increase. Now, whether it's a linear increase or a non-linear increase, it's a non-linear increase, because there is no direct relation between how much is the amount that is the bond length is increased and how much is the difference in the peaks. Okay, so the next question we have is from GATE 2020 or this year. This was a 2 marks question, and the question says, assuming no interaction between vibration and rotation energy levels in HF, so the molecule is HF diatomic, the frequency of R branch line originating from J equal to 4 in the IR spectra is, now they have given B equals to 19.35 and they have given you the fundamental mu naught is equals to 4138.52. Now this is actually this entire thing. Okay, now if they explicitly give you Xc, then you can use this formula, or else consider this to be the vibrational energy. Now in that case, what you would get is, you want to find the J equal to 4. Now let's say I'm doing it in the R, so this is 2B, 4B, 6B, 8B, 10B. This is 0 to 1, 1 to 2, 2 to 3, 3 to 4, 4 to 5. Now this is one way, or else, now this question does not concerns this case where there is a breakdown of bond number approximation, but the previous case. So that means that would mean mu naught, I'm considering this here, plus 2bj plus 1. That would mean 4138.52 plus this is 4 plus 1, 5, 5 is a 10, 10 into this is 193.5. So this should give me a value of 2, 0, 2, 2, 3, 4. So the question says to round off to 2 places, so we can just remove this and this should be the answer, and I think this was the answer, 4322 centimeter inverse. Okay, now in this lecture we have only considered diatomic molecule for the discussion of vibration rotation spectra. In the next lecture we'll see the vibration rotation spectra of polyatomic molecules, and followed by the effect of nuclear spin statistics on the vibration rotation spectra. Now one thing I would like to mention, that while I just realized few days back that I had not discussed the questions of IIT-JAM for the last 6 to 7 years when I was doing the discussion for vibrational spectra, while I had done that in the rotation spectra. So in order to compensate for that, after the end of vibrational spectra, I'll make a summary video for all the important equations, important assumptions and facts that you should remember before going to the exam. In that particular lecture, I also discussed 5 to 6 questions that have come from the vibration spectra of vibration spectroscopy of the diatomic molecules or polyatomic molecules. In that lecture, I'll discuss all of them. In case you have any queries, in case you have any doubts in understanding any of the topics or any question, you can always put them down in the comments. I'll surely clear them up in the upcoming lecture.